Hey, Matthew, here we go. We got our last lesson on factoring, lesson 4.1.5, factoring special cases. So we're going to just look for some special patterns that we see in factoring. To start us off, we've got a whole bunch of factoring problems here. So A through L, holy cow. So there's a lot of them. So what I'd like you to do, if you're just kind of following along at home, is just try these out yourself. I'm going to pause it in a second and kind of set up all the problems, but see how you've improved in your factoring. Factoring is super important for your next math classes that you'll be taking. So it's really important that you learn this skill. So try it yourself and pause it real fast. And I'm going to set them up, and I'll be back in a second. All right, so I'm back. I have set everything up. I've got my area models. I've got my diamonds. I'm ready to go. All right, let's see how you did. So for this one, I've got my x squared, and I've got my negative 49, but there's no x term in the middle. That means these two numbers have to add up to 0. So that adds up to 0. And then remember, these two numbers, the diagonals multiply to give us the same as these diagonals multiplied. So this is negative 49x squared. Okay, so what has multiplied to give us negative 49x squared and add to give us 0? Well, the only thing that can be is positive 7x and negative 7x. That multiplies to give me negative 49x squared, and it adds to give me 0. So I'm going to put 7x here and negative 7x right there. All right, so finishing it up, this should be x and x. This is going to be negative 7. This will be positive 7. Does it multiply to give me negative 49? Yes, everything's working. So this is x plus 7 times x minus 7. All right, next one. I'm going to put the x squared here, the negative 24 here. So multiplying these two together, I get negative 24x squared. And then these two have to add up to 2x. So what multiplies to give me negative 24 and adds to give me 2? Well, one of the numbers has to be positive, one of them has to be negative, because that's the only way I'm going to get negative 24 when I multiply them right there. So let's think of those numbers. 6 and 4, I think. So I think the 6 has to be positive, and the 4 has to be negative. So 6x minus 4x, that's 2x. Everything's working out. So I'm going to put them over here. 6x, negative 4x. All right, so now I split it up. X and x. This should be 6. This should be negative 4. So it looks like if it multiplies correctly, so this should be x plus 6 times x minus 4. Awesome. Next one. So x squared goes here, 25 goes here. They multiply to give me 25x squared. And they are adding to give me negative 10x. All right, so what multiplies to give me positive 25 but adds to give me negative 10. Now, the only way that's going to happen is if both the numbers are negative. So I think my two numbers have to be negative 5 and negative 5. Because when you multiply those, you get a positive, but when you add them, you get negative 10x. So negative 5x, negative 5x. Here we go. X, negative 5, negative 5. So this is x minus 5 times x minus 5. We can write that as x minus 5 squared. There we go. Moving on. All right, next one. We're going to put 9x squared up here. Oh, by the way, we should be looking for a GCF first, a greatest common factor. I looked ahead. I don't see any GCFs on this one. So we're not going to factor more than once on these problems, but you should be doing that as you go through. Always double check first to see if you have a GCF. And there wasn't any. I looked already. All right. So these multiply to give me 36x squared, and they add to give me that 12x right there. All right, so what multiplies to give me 36 but adds to give me 12. I think that's 6x and 6x. All right, so I put 6x here, 6x here. I think I'm going to need to split this up into 3x and 3x. All right, then this number down here becomes 2. And this number becomes 2. So kind of like that last one, it's 3x plus 2 times 3x plus 2. That is 3x plus 2 squared. Next one, 5x squared goes here. Negative 1 goes here. Multiply those, we get negative 5x squared. When we add them, we get negative 4x. So what multiplies to give me negative 5, but adds to give me negative 4. That should be negative 5x and positive 1x. So we got negative 5x here, positive 1x here. So this should be 5x. This should be x. This would be negative 1. And this would be positive 1. Do they multiply to give me negative 1 over here? Yes, they do. I've got my factors. I've got x minus 1 and 5x plus 1. Moving. All right, so 4x squared goes here. Negative 25 goes here. Multiply those together, we get negative 100x squared. But there's no x term, so that means they add to give me 0. There's only one way to do this. That would be to have a positive 10x and a negative 10x. Those cancel each other out. We get 0 right there, but they do multiply to give a negative 100x. So I'm going to put 10x here, and I'm going to put negative 10x here. Splitting these two up, I'm going to split them up into 2x and 2x. This one's going to be positive 5, and this one will be negative 5, because 2x times negative 5, negative 10x. So this one splits up into 2x plus 5, 2x minus 5. All right, halfway done. Next one. I'm going to do x squared here, 9 here. Multiply those. We get 9x squared. The middle term is what they add up to, negative 6x. So what multiplies to give me 9, but adds to give me negative 6? That should be negative 3 and negative 3. So I put them over here. Okay, and so I split this up into x and x. Over here, this should be negative 3. This one also should be negative 3. They're both the same, so this is x minus 3 times x minus 3, or x minus 3 squared. Hopefully you're starting to see the patterns here. This is x squared, this is negative 36. So this is negative 36x squared. This is 0 because there is no x term. So that should be negative 6x and negative 6x. No, positive 6x. Wow. Knew something looked wrong there. All right, so x and x, negative 6, positive 6. We get x minus 6, x plus 6. This one, we've got 7x squared here, negative 3 over here. Multiply those together, we get negative 21x squared. The diagonals have to be equal to each other, so I know that these two are going to multiply to give me negative 20x squared, and they have to add to give me negative 20x squared. Not x squared, just x. Okay, so this is negative 21, and this is positive 1x. Okay, so I'm going to put, it doesn't matter where you put them, I'll just put the negative 21 here, and the positive 1x here. So I need to split these up. I'm going to split it up into 7x and positive x there. So 7x times negative 3, and then x times 1. So yes, they multiply there, so that's looking good. So we've got x minus 3 times 7x plus 1. Whew. All right, almost there. Okay, so next one, we put 4x squared here. 25 here. They multiply to give me 100 x squared. This number is what they need to add to. So what multiplies give me 100, but adds give me 20. That would be 10x and 10x. So I put a 10x here, put a 10x there, and I'm going to split this up into 2x and 2x. This will be positive 5. This is positive 5. These are the same. So this would be 2x plus 5 squared. Next one, we've got x squared plus 4. They multiply, give me 4x squared. They should add to give me 0. So what multiplies give me 4x squared but adds to give me 0? You may be tempted to write 2x and negative 2x. But these do not multiply to positive 4x. These multiply to negative 4x. So that does not work. You know what? There is no combination. There's no combination that multiplies to give us 4 but adds to give us 0. That's just not possible. I mean, you could try negative 2 and negative 2, but that would give us negative 4 down here, not 0. So this one is not factorable. Or prime. Prime just means that it's factored as far as it can go. This doesn't break down to anything else. Last one. 9x squared, negative 1. Multiply those. We get negative 9x squared. They add to give me 0. This one does work because we could do 3x and negative 3x. Because they multiply to give me negative 9, to add to give me 0. So I'm going to put 3x here, negative 3x here, split them up. So this is 3x, 3x. This will be plus 1. This will be minus 1. So this one factors into 3x plus 1, 3x minus 1. All right, so we're going to look for patterns here. Which ones can we group together because they have the same pattern for factoring? Well, the first pattern are these binomial problems where we have two terms. And it looks like they've always been turning into x plus 7, x minus 7. So there's like the same binomial except one's positive, one's negative. So A was the same for that one. Where's the next one? F was the same for that one. H was the same for that one. And L. Now K almost, except look at all these other ones, they had a minus sign with the second term, but this one had a plus sign and it did not factor when that happened. So those, how many was that? 1, 2, 3, those 4, this one, this one, this one, this one, they all have a pattern together. Now there was a second pattern out there. The second pattern was when they turned into perfect squares. X minus 5 squared, 3x plus 2 squared. Where's the other one? G was x minus 3 squared. And J was 2x plus 5 squared. So there's a second pattern that we're seeing. Now there's actually a third pattern that maybe you've noticed before. Look at B. When you look at B, it doesn't have a leading coefficient. There's no number in front of x squared. So when we split this up into negative 24 and 2, and we got 6 and negative 4, we did the area model, but we really didn't need to. We can just put the 6 here and the negative 4 right there. Were there any others like that? Let's see. Nope, there weren't any others like that. I mean, this was kind of like that, G, where we had what multiplies, there's no leading coefficient right there. What multiplies give me 9, adds give me negative 6, it was negative 3 and negative 3. I really didn't need to do the area model. Negative 3 and negative 3 were my two constants in my factors there. Same with, wasn't there another one like that? Yeah, C. Over here on C, no leading coefficient. We got -5 and -5. Well, -5 and -5 were the two numbers there. We really didn't need to do the area model. So that's kind of another pattern that we might be seeing, but we're going to focus on these other patterns. So we're going to focus on this other one first. So we noticed that when there were two binomials like this, that they followed a pattern. And notice in all of these are perfect squares. X squared, that's x times x. 49, that's 7 times 7. Over here, that's x times x, that's 6 times 6. Over here, this is right here. This is 3x and 3x. This is 1 times 1. So there's a pattern to that. So what I see here is that this number is 5x times 5x, and this number is 1 times 1. And in the patterns that I saw before, like just take this one, see it has perfect square minus perfect square. It was 3x plus 1, 3x minus 1. So the pattern for this one should be 5x plus 1, 5x minus 1. Let's find another one like that. This one right here. So this one, perfect square, perfect square. Yes, that's the perfect square of 3x. And yes, that's the perfect square of 10. Is there a minus sign in between? Yes, there is a minus sign in between. So this one factors into 3x plus 10, 3x minus 10. That's the pattern that I noticed up there. Just like this one. This is a perfect square of 3x. This is 1, so it's 3x plus 1, 3x minus 1. Now this one has two terms in it, but it's kind of like this one where they were both positive. This one doesn't have a negative sign in here. So we saw on the pattern it's not going to work out. So this one's not going to be factorable. Even though this is 3x times 3x and this is 2 times 2, we notice it does not have a negative sign. So I can't factor this one. This is not factorable or prime. All right, so that's one of my patterns. My second pattern was with my perfect squares. Let's look for our perfect squares. Okay, so x minus 5 squared. Now what I noticed here, this is x times x. This is 5 times 5. And look what it was, x minus 5 squared. Now this only actually works when the middle term is 2 times this x times this 5. 2 times x times 5, 10x. And the negative sign here makes this the negative right here. Let's look for another one. Here's this one. This is 3x times 3x. This is 2 times 2. And this middle term is 2 times 3x times 2. 3x times 2 is 6x, times 2 is 12x. And look at the pattern, 3x plus 2 squared. All right, let's finish these off. This one follows that pattern. This one is the perfect square of x. This is the perfect square of 4. And this middle term is 2 times x times 4. X times 4, twice that amount, that's that one. So we can say x plus 4 squared. Didn't even have to do the area model. Beautiful. This one right here, this is the perfect square of 3x. This is the perfect square of 2. This middle term right here is 2 times 3x times 2. 2 times 3x times 2 is 12x, so it looks like it's working. So I've got 3x minus 2 squared. And then our final pattern is this one right here. This one doesn't have a leading coefficient right there. So our pattern for this is I would just do the diamond, negative 36, and then negative 5 here. So it multiplies to give you negative 36, but adds to give me 5. That would be negative 9 and positive 4. They multiply to give me negative 36. They add to give me negative 5. And since there's not a leading coefficient, I don't need the area model. I can just write my two factors as x minus 9 and x plus 4. Hopefully we've seen those three patterns on what we were doing up above. Okay, that looks really pretty. I'm going to put that on my refrigerator at home. All right, back to here. Okay, so that first pattern, we're going to call it the difference of two squares. Anytime you got two numbers that are squared and there's a negative sign in between them, difference means subtraction, squares means they're numbers that are squared, we're going to get a plus b times a minus b. We're going to show that this pattern works in an area model. So if I do a plus b times a minus b, this is a squared, this is ab, this is negative ab, and this is negative b squared. These are my like terms. One's positive, one's negative. They're canceling each other out. And yes, I do get a squared minus b squared. So using that pattern, this is the perfect square of x. This is the perfect square of 12. So this one should be x plus 12, x minus 12. This is the perfect square of 4x, 4x times 4x. This is the perfect square of 9. There's a negative in between. So that one factors into 4x plus 9, 4x minus 9. This one, oh dear, what did I do here? That is 20 times 20 and x squared times x squared. So that's 20x squared. This one, this is x to the third times x to the third, and this is y to the fourth times y to the fourth. Because remember, when you multiply the exponents, you just add the, when you multiply terms with exponents, you just add them. Okay, so there is a negative in between. So this would just be 20x squared plus x to the third, y to the fourth, and 20x squared minus x to the third, y to the fourth. Those still factor, but whatever. They still have a GCF in them. Okay, our other pattern was a perfect square trinomial. So in this one, remember I was saying 2ab in the middle. So for this one, if I do a plus b times a plus b, we get a squared, ab, and b squared. Now this time, the like terms are not canceling. There's two of them. There's two of the a times b's. So that's why on this one, I was saying that there's the middle term is 2 times this times this. There's two of them there. Same thing with this one. It's 2 times x times 4. All right. So we're going to use that pattern. This number right here is x times x. This number here is 12 times 12. And then we double check to make sure that this number is 2 times x times 12. And is it? Yes, it is. So I can do x plus 12 squared. Let's look at this last one. This is the perfect square of 4x. This is a perfect square of 5. This middle term is 2 times 4x times 5. 2 times 4x is 8x. 8x times 5 is 40. So it's working. So this one is 4x minus 5 squared. Do you have to memorize this pattern here? No, but it makes factoring some of our problems much faster than using the area model and the triangle. Do you have to use the difference of two squares? No, because you can still use the area model and the diamond. But once we notice these patterns, we're going to want to, especially when you move on in math, you're going to want to learn how to factor fast and not take up a whole bunch of time by making all these area models and diamonds. So noticing these patterns is super important. Closed set polynomials, I just think it's stupid. We're not going to do it. I don't know why they added it. Anyways, all right, so there we go. 4.1.5. That was a long lesson. Sorry, that was a lot of problems. All right, math hard. See you guys later. Bye-bye.